take a picture, you take a picture. It's over there. All right. Well, I think I left my black pen on here. If you see this smartboard marker on the desk, let me know. I might put it down somewhere. Okay, when the first derivative is positive, what do we know about the function? Oh, thank goodness. It did say increasing, right, the first time? If the first derivative is negative, the function is? If the first derivative is changing sign from positive to negative, max. It's got a relative max, the function. And if the first derivative is changing sign from something to negative to positive, the function has a min. I'm sorry if that's not entertaining, but now is where it gets entertaining. Okay, people are like, oh yeah, we got this. Now it's shifting things. If we know the second derivative is positive, what is the first derivative doing? It's got to be increasing. This is the same relationship here. You see that? Anytime any function is increasing, its derivative is positive. Don't ruin it. Okay? If this second derivative is negative, the first derivative is decreasing. If the second derivative is changing sign from positive to negative, the first derivative has a max, a relative max. I like the blue. And if the second derivative is changing sign from negative to positive, the first derivative has a min. You see that, guys? So it's the same relationship. We just kind of took this relationship between f and f prime. We just shifted it over there to f prime and f double prime. All right. If you look at the next set, I really did something dumb when I made the sheet. I said the yellow boxes. You guys don't have yellow boxes. I don't know. Yeah, we'll get back to the homework in a second. But one more. Okay. So we had this on, before. This is all the same. If you only know the sign of the first derivative, you can tell me about the function, like we said. Okay, that's all great. But you will never know anything about the second derivative from the sign chart of the first derivative. Nope. Never. Well, you just don't know. You just make the question mark. But for the second set here, when we had, if we're given the sign of the second derivative, not only can we say what's going on with the first derivative, nice, I know, I should have designed it better. I'm thinking that as I'm doing it. And then I said fill in the yellow box, so you guys can't see yellow. So that was, I know, I'm sorry. I just, they can't all be winners. But we can fill in these. We can, from the sign of the second derivative, determine something about the function. So if the second derivative is positive, because our slopes, our first derivatives are increasing, what's it mean about the actual function? Concave up. Looks like a cup, right? All right. If our second derivative is negative, because the first derivative, the slopes are decreasing, or our function is, what's that? She's on this cruise ship now, and now she thinks it's snowing here, and she's laughing, throwing her head back. The light. All right, if the second derivative is positive and it changes to negative. All right, so our first derivative has a max. That's what's going on with the actual graph? If the second derivative is changing from positive to negative. What does it look like? Like when it's positive, what does the graph look like before it changes? If the second derivative is positive, oh yeah, you do. When the second derivative is positive, so your function's concave up, right? So it's kind of happy, it's happy, it's happy. Oh, it changes to negative, the second derivative, oh, I want to keep that smooth. Oh, so then it changes, right? So it's concave up and then changes. So that point here where it changes concavity has a special name. Has anyone ever heard the word inflection? Oh, sorry, I have a bad memory or something. Okay, well, it's like a bending. So where the concavity changes, that point is called the point of inflection. Now, the second, so that's this point right here. So I'm just going to write a pi right here because I can't write all that in that little space. So that would be the point of inflection. What about if the second derivative is changing sign from negative to positive? What would the graph look like? Okay, it would start out being concave down, right? It starts out sad, and then it goes up. So at that point, it's still a point of inflection. It doesn't matter, whether it's changing from concave up to down or down to up. What we have there is a point of inflection. That wasn't real. Okay. So, when the first derivative changes sign, the order matters. Positive to negative, you got a max. Negative to positive, you got a min. When the second derivative changes sign, you just got a point of inflection either way. Okay? Yeah. Very cool. It was very exciting. I know. All right, let's go check the homework. Oops, too far. Now, I'm sure you didn't give the y coordinates, so don't worry about the y's. And I'll give you the answer to 12 separately, because that one I probably should have just omitted. If you're getting a whole bunch wrong, it's probably because you were looking at those graphs and you thought that that was the function instead of the derivative or something. I don't know. Or Jen gave you the wrong answer. She was sleepy when she did it, so you can't really, this is not going to be your finest work. No, I'm recording. Jen's trying to tell me a funny story. It's not appropriate. We'll pause later. Make sure you got these answers down. So if you only gave the x coordinates, don't worry about it. That's what you were going to give. The y's, if you want to give the y coordinates of points, you have to plug the x back into the original function. If you're wondering, where did those y coordinates come from? What's wrong? Are these really bad? Oh no, did you get any right? One right, okay. Well, it's better than 0, right? Okay. Well, let's investigate what happened. Let's take a look at a couple of these things. And as far as 12 goes, once you guys have checked these, I'll show you the answer to 12. 12 was very difficult. What did you get? What are your critical values for 12? Okay, yeah, that's what I thought. No, 12 was tough. You could have maybe looked at the graph and tried to see if, there are any corners or where the derivative was 0 to get the critical values, or else you had to write a piecewise function. It would get tough. Anyone still checking this stuff? You didn't have to give the y values. Okay. Anyone still checking? I just got to make sure I finish this. Oh, sorry. I was going to give you the answer to 12. Oh, 12, you had the graph, so you know what it looks like. If you had just y equals x squared minus 9, it'd be this parabola. Y equals x squared, move down 9, right? But once you put the absolute value around it, wherever it's negative, no, not really, but wherever it's negative, it flips it over the x-axis. So it looks like, well, it kind of reminds me of like Batman or something. I don't know why. So the critical values are negative 3 and 3, because the derivative doesn't exist here, and at 0, because the derivative is 0 there. You get a horizontal tangent. Well, that's kind of neat. What I did when I did it, I actually wrote this as a piecewise function. An absolute value is equal to what's inside when what's inside is positive. And x squared minus 9 is positive if x is greater than 3 or less than negative 3. So I made it x squared minus 9 when x is less than negative 3 or greater than 3. And if what's inside is negative, you take the opposite of what's inside. So I just negated it. I know. No, like, I think we don't do enough with absolute values. The absolute, yeah. Okay, but what did you do to get rid of those? Oh. Well, then I took the derivative of each piece. I took the derivative of each piece, and I checked out the value of the derivative at you know, each of these transition x's. So don't worry about this one. We got to do more work with absolute value. It's not that big a deal. But if you did make a sign chart using negative 3, 0, and 3, you have a min at x equals negative 3, a max at 0, and a min at 3. Yeah, it gets a little involved. Okay, but with the normal questions, what do you got? Which ones do you want to go over? 7? Okay. That's when you couldn't factor. Oh, yeah, that's right. You were just showing me. It didn't catch the mistake. Oh, it came out to be an irrational number? What was the answer for 7? Oh. Oh, so they were rational, so we could have got it by factoring. Okay. What was the function again? And what? Okay, so you got the first derivative, 6x squared minus 18x plus 12. So it's always defined, so you just want to set it equal to 0. And this is where we got trouble. So I know you pulled out the 6, right? So you pulled out the 6, and you have x squared minus 3x plus 2. Oh, yours didn't look like that. You still got to run? You got this? Okay, so let's factor. So when you factor that, what are the factors? We set the factors equal to 0 and solve, and we get our critical values of x equals 2 and x equals 1. I have to say, when I looked at your paper, I didn't see where the mistake was, so I feel your pain. After that, is there any question, or was just that, right? So then they're positive, negative in here. Okay, what other ones do you want to go over? Yes. 6. Can you just read me what the function was? Oh, a graph. Oh, a table, okay. Chart. Nah, I got it. Thank you, though. Okay, so they give you the values of the first derivative at different x values. At 1, 2, 3, 4, 5, and 6. So they tell you the first derivative. Oops, I missed one. That's a 0. It's an important one. Negative 4, negative 8, negative 12. Okay, and you can't just ignore all the words because it says various values for the derivative f prime of x of a differentiable function are shown in the table below. If f prime of x always decreases, see how the f prime of x values that you see are decreasing? Okay, what that's telling you, you don't have to worry that in between x equals 1 and 2 that the derivative goes from 8 down to negative 7, back up to 4. You know that it's just always decreasing. It's kind of like what you think it's going to be. The derivative's just decreasing. It's not doing some kind of crazy little dance in between each of those. All right? It's always decreasing. All right, so that's just like telling you, all right. And then it says, which of the following must be true? Now, if you look at the choices, Max and mins, that's when the derivative changes sign, right? When the derivative is 0 undefined. So you can see the derivative is 0 at 3, and it's changing from positive to negative. So if you would actually graph this, you know, at x equals 3, the derivative is 0, but at 2 it's 4, so somehow it's just going down like that. So the derivative is changing from positive to negative at 3. So it's a max. Other questions? 3? Find where it has a relative max. The function is g of x equals 4x cubed. I wonder if you left off an exponent. Okay, so we're looking for a max of g, so we get the first derivative. And I'm sure you got that, right? And then what'd you do? Okay, set it equal to 0, and you pulled out a 6x. Nice. What's the other? That's right. Okay. X equals. Okay, so you got the right critical values. All right. All right, so I'm trying to see where the mistake is. So we make our little g prime. Let's take a number greater than a half. How about 1,000? G prime. Okay, any number greater than a half, we're all going to get the same answer. The first factor, positive or negative? How about the second factor? So the product is 2. All right, here's the thing I bet. Give me a number between 0 and a half. Let's do 1/4 or 4. All right? Okay, so I'm going to say g prime of 1/4, right in the middle. How safe. All right, 6 times a fourth, is that positive or negative? How about 2 times the fourth minus 1? Negative. So with positive times a negative. You got that too? You just want to like let the class know that you did everything right? All right. Or maybe the answer key was wrong. So maybe the answer key is wrong. You guys are the first one to notice it. Let's pick a number less than 0. They're both going to be negative, right? So the product's positive. Okay. The question is, where is there a max? At x equals 0. And was that the answer I had? Oh, okay. So good.
You picked the wrong number.
Okay. That's negative. No, negative times negative, positive. Okay, so that would be negative. Okay. Oh, I think you were like multiplying these instead of subtracting the 1 from your -2. I think that's why. Okay, cool. You got one? We got time for one more. You got another? Yes. Wait, Nicole. Which one? 9?
Ashley, she wants to do number 9.
Oh, I'm so glad you asked this one.
Probably not.
Okay.
Oh, I'm not. No, not at all.
No, but here's the thing. I know, looks crazy. But guys, tell me that you use the product rule. You got the product. So you got this line here? First times derivative of the second, little chain rule, plus the second times derivative of the first. Yeah, derivative of the first. So you have 2 chain rules inside of the product rule. This is the derivative, and we set it equal to 0. Yeah. Yeah, what I've underlined, I want you to see there are only 2 terms here, right? How are we going to see where all this junk equals 0? Well, we always factor. Now, it might look difficult, but there's a GCF in these 2 terms. You got these 2 giant terms here, and they have a common factor. And that's what you want to pull out. See how both of them have an x minus 3 squared? So that's a GCF. And then the other common factor, we got an x plus 2 and an x plus 2 squared, so x plus 2 goes into both terms, right? Well, now it has to. Because when you're getting a derivative with the product rule, you know it's going to be this big sum, right? And if you have to set it equal to 0, you're going to want to factor it. Well, GCF is probably going to be the only way to go with that. So just try to remember that next time. Now, what's really cool, once you pull out the x minus 3 squared and the x plus 2, and you write what the other factor is, when you clean it up, this other factor works out to just be 5x. So this first derivative is just x minus 3 squared times x plus 2 times 5x. Now we're on easy street. We get our critical values. 3, negative 2, and 0. Boop, boop. What is that squared telling you? It's bouncing at 3. No sign change at 3. And indeed, that is what happens. So then after that, it's fine. I know where you guys had the problem. It was just trying to get this derivative equal, setting it equal to 0 and solving that. I think my smartboard pen on here.
I tried to look for it. It's missing. Oh, there it is.
Oh, you look really hard.
I'm not good at really well.
All right, let's talk about today's stuff, right? Oh, I can't do the juice box, so I feel like I'm going to not make it. Okay. Okay, the sign of the second derivative, it's all about the concavity. So the thing is, if someone asks me where's a function increasing, decreasing, max, min, I'm making a first derivative sign chart. But if someone asks me, hey, where is your function concave up, concave down? Where do you have a point of inflection? I don't want to know the sign of the first derivative. You're going to make a sign chart for the second derivative. All right, so play along with me here. Label your first derivative. Let's pretend we made a first derivative sign chart and we label it A and B. And let's say we got our first derivative, we got our critical values A and B, and we found out the signs went positive, negative, positive. Right? So we did all that work, and you guys have made first derivative sign charts. Now what I want you guys to do is interpret that. Tell me what that tells you about the function. This is your first derivative sign chart. How about this first interval? Increasing. How about the second interval? Decreasing. And the last interval? So not only do you now know from your first derivative sign chart where your function is increasing and decreasing, what's going on at x equals a? This is the first derivative sign chart. Max. Okay, if the first derivative changes sign from positive to negative, your function's increasing and decreasing, you have a max. It's the fog. It's making us all a bit foggy. What's happening? All right, how about at B, where the first derivative changed sign from negative to positive? Please tell me I wasn't allowed to guess. Okay. We have a min at x equals b. So this is the information that we can glean from our first derivative sign chart, right? Bam. All right, now let's say I got my second derivative and I made a sign chart. Somewhere on your second derivative sign chart, let's label it, put a C there, and let's put a D. That's crazy, crazy different. And let's say the pattern this time for the signs, when I plugged in my values into my second derivative, it goes negative, I'm changing it up, positive, oh no, I'm not changing up that much, negative. Let's not be radical, let's just keep it, So now I know the sign of my second derivative for all these values. Now I want to interpret the results. Tell me about the function on this first interval. Concave down. Oh, don't say concave down, a clown, because people think of a smile. That's going to confuse everybody. Oh, no. Oh, no. This is how these little tricks get all messed up, like that whole pie thing. No one remembers what pie is delicious. You know, clowns, are they smiling, they frowning? No, no, that's, no, you just gotta, no. No, area is measured in square units and circumference is not. So. All right, let's keep this together here. All right, the second interval from C to D, second derivative is positive, so my function is concave up. The interval from D to infinity, concave down. Now what's going on at x equals c? Nice. We've got a point of inflection. I'm writing the inf at x equals c. How about at x equals d? Another point of inflection. Okay. So depending upon what you're asked for, you make the first or the second derivative sign chart. Okay? So let's try one. Yes, 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 yes. Example A. We've got this function. Look at those numbers. Love it. And look at what we're asked for. We want to know where the function's concave up, concave down, points of inflection. What should we do? Yep. Make a sign chart for second derivative. Don't even bother making a sign chart for the first derivative. You're not asked where it's increasing or decreasing. All right, so do that. Get the second derivative. Don't be afraid of fractions. Go. Oh, yeah, okay. All right, kids, we just got back and I forgot to record, so. Our second derivative equals to 0. Solved it. Critical error. Summed it in. And made a sign chart. And it's concave up 7/3 to infinity. Concave down negative infinity 7/3. Point of inflection at x equals 7/3. Okay, sorry that was fast. I forgot to record it. All right. Anyone get any critical values for this one? 0. And this is a weird one, right? Because, oh my goodness. When you get that second derivative is 12x squared, it's always positive. So what does it mean about the function?
It's always increasing. It's always concave up, yes.
Just said it's always concave up. This is one happy function. So yeah, where's it concave up? You can go right from negative infinity to infinity if you want, because it doesn't change sign. To be a point of inflection, you're looking for a sign change in the second derivative. As far as where's it concave down, nowhere. You can write NA, not applicable, or never, or, you know, nowhere. Just for the sake of the kids at home, I am going to show the last one, because the last one, you can pause if you're at home. I'm going right to the answers. You get the second derivative, you rewrite it as a fraction, negative 2 over 9 cubed root of x to the fifth. It'll never equal 0, but it's undefined at 0. You have one critical value. And what that tells you, it's concave up from negative infinity to 0. And if you think about the graph of the cube root of x, that makes sense. It's concave up from negative infinity to 0. And then it's concave down from 0 to infinity. And the point of inflection is at x equals 0. All right, kids, have a good one. Remember the book's here if you have to take a picture for the homework. 799, I believe. It's open.
That was a good story about
Sydney's good story about your cup.
She's like, I'm drinking
No. The first derivative tells us where the intervals where a function is increasing, where it's decreasing, intervals of increase and decrease, and it also tells us if we have any extreme values. Second derivative tells us, gives us the intervals where a function is concave up, concave down, by, and if we have any points of inflection. And that we'll call it a day.